Sorry about that interruption, everybody. Sounds like that siren has moved on, so let's continue. And we're just about done with section 3.3. So again, we're seeing our histograms still look like bar graphs, just that these are bar graphs that specifically go with numerical data, and that we're organizing this data some way so that when we group it, so whether it's just every individual data value, that it's clear what the bars represent. When we group it over multiple data values, we're clear what we are including. That's really it. And outside of that, it's a bar graph. So what else do they discuss here? This is where we just start to get, two things. I mentioned the idea of ideally getting these class sizes to be the same so that we get equal width on our bars. Every once in a while, it makes sense to not do that, but then you would just have to be clear, the corresponding bars on the histogram would have to clearly show that these are not the same size. So they do an example of this quickly looking at debt. And again, I'll do it with car mileage. If we wanted to look at how many miles are on your car, and then we had one was 0 to less than 10,000 miles, but then my next one goes from 10,000 to 50,000 miles, and then I go to less than, and then we'll go 50 to less than 90,000, and then we'll just finish this last one, 90,000 to less than 100,000. These first one and the last one are basically 10,000 mile classes. These two in the middle are 40,000. So it's very quick and easy to ignore the numbers part and just go 0, 10,000, 50,000, 90,000, 100,000. And no, I'm not even putting the frequencies here. That's not my point in this one. And we get something like that, but that would be misleading. It's giving me the frequency totals fine. I could still go over and try and measure exactly what they're corresponding to over on the frequency side to know how many people have a car whose car mileage is in that vicinity. But this is the problem. All these are the same width bar, and I really should have the less than part that I'm coming a little short, but the issue is the size of the bar. And if you appropriately label the x-axis, I'm just going to stop here, that would be clear. Now if I go 0 to less than 10,000, just short of the 10, let me make this clear, this is in thousands of miles. So the 10 really represents 10,000. So I get that as my first bar. The second bar would start on the 10 and go all the way out to here. This would be the accurate way to represent that second bar, not this. But again, that's a little weird. Why would you do that? There could be a couple of good reasons, but mostly this comes up again in the misleading statistics part. People try and hide that they're expanding a category to try and show off something that happened there, but they don't show the wider bar to make it clear. Like, just looking at this, doesn't it make sense to have more cars in this category than here? It covers so much of a broader range. So without even looking at the frequency totals to say how many more there are, but just the fact that it does make sense there are because you're covering so much more of a gap. It's like, again, if I wanted to classify our class according to shoe size, and I took everybody who had a shoe size smaller than 2 and put them in one spot, and everybody that had a shoe size from 2 to 10 and put them on the other side of the room, we better bet there's going to be a lot more people who have a shoe size 2 through 10 versus just a shoe size of 1. So, again, just trying to make that clear. It could happen, but that's a little strange. The rest of 3.3, we start to talk about the different type of histogram shapes. So after we have these square rectangular bars, you'll notice how we start to try and put a smooth curve on top to try and represent what we are seeing. Now, how do you actually fit these curves on? Again, we'll get a little further along, but what we want to point out right now is there are a few distribution shapes we should be aware of. This one isn't quite perfect, but this very first one has what we call a bell-shaped distribution. Eventually, let me make that note, this is bell-shaped. And then down at the bottom here, that is that idea of bell-shaped. Eventually, we'll talk about the normal distribution as one example of a bell-shaped distribution, the normal curve. But in general, we want to start recognizing that this bell-shaped distribution, very common. Most data falls in the middle. The further you get away from the middle on each side, the less data we have. There are so many things that fall into this type of situation. You talk about IQ, that's what happens. You get 100 in the middle. Most people right around that 100 IQ score, a little above, a little below. And then people who are much lower or much higher than that, fewer people, no matter which direction you go. Same thing with height or weight or shoe size. For men in North America, the average height is 5'9". Okay, so that's where most people are. Someone who's 5'9", we stack them in the middle. Someone who's 5'8", someone who's 5'10". Lots and lots of men in that vicinity. When you start going to the extremes, someone who's 6'5", a man who's 5'1", you start going to those extremes, you get fewer people on both of those extremes. So that is our bell-shaped or our normal distribution. Want to be careful. We don't want to just automatically see that and assume all these are normal. But that's, like I said, why I wanted to introduce the term bell-shaped. The other thing we have to be aware right now is the idea of right skewed and left skewed. For me, I gotta be honest, it's kind of the reverse of what I always think. The book also talks about a positive or negative skew. I've never really seen that terminology outside of this exact book, but right and left skewed, that comes up a lot. So if we talk about a positive skew, a right skew, to me that's kind of funny because a right skew is where the big bubble, where here like the bubble in the bell curve or in the normal curve, the bubble is in the middle with kind of that like equal tail off on both sides. Right skewed, the bubble is actually on the left side and you're flattening out the further you go to the right. And then left skewed is kind of the opposite. The bubble is on the right side. So this would actually be an example of something that is left skewed. This one is not really right skewed because that bubble is not really to the left. We don't know what else is going over here. But if we knew a few more categories were really tiny over here, then that might give us more of that, right skewed. So left skewed if the bubble's on the right, and right skewed if the bubble is on the left. So that, again, a few other good examples just to read through, just to see a few more histograms, but that gets us through section 3.3. We'll continue moving into 3.4 in this video. 3.4, we very specifically start looking at bivariate data sets. We started off talking about categorical data, saw how we could still compare different data sets, but still based off data that is categories. Saw how we could expand that to when we start getting numerical data, but all those were still univariate, one variable, one data value. But now if we start getting bivariate numerical data, we want to say a few quick things here, but then this comes up, I believe it's chapter 5, if I remember correctly, that we get a little bit more. So we'll get another chance to look a little deeper into this. But there's several things we want to say here. The first thing is if you have bivariate data, specifically bivariate, again, two components. When we have two components, we treat it like it's an ordered pair, like it's an XY pair. So just a quick example. Maybe I want to ask you, what was your grade on your last exam? But I'm not just asking you for that one piece of information. I also ask you for how many hours you studied. You're giving me two pieces of information. That's bivariate. I'm treating the grade like the X value and the hours of study like the Y. The funny thing, when we get a little deeper into this, what should be X, what should be Y, we will remind you that the X is typically treated as the independent variable and the Y is the dependent. Y depends on X. So when we get to this section, I'm not going to try and trick you on this part. We always make it clear how we want to look at it. But if you were ever doing it for yourself, this one would probably make more sense in the other direction, that X should be hours of study and your Y should be your grade. Because thinking about it, you control how many hours you study, and the grade you get depends on how many hours you studied. Now, there's other relationships that are not quite that clear. If we want to look at the relationship between height and shoe size, there are things we can guess, or other things like how many years at your job compared to your salary. This one is more like this one, and that we could probably guess this would be the nature of the relationship, and that we would guess something like the longer you're at your job, the higher the salary you would receive, and that would be the connection between those two. But that may not necessarily be the case. It's possible it would go the other way. But in this situation, height versus shoe size, is it your height is independent and then your shoe size depends on how tall you are? Or is it your shoe size is independent and how tall you are depends on your shoe? The answer is probably neither one of those is correct. So that would be a little harder to separate. But again, not trying to bust your chops on that, just trying to point out several different scenarios where we would want to have these two pieces of information together. And that would give us a bivariate data set. So once we have data like that, our main way of representing that data is a scatter plot. That's all there is to it. We would just plot those as XY pairs. So let's stick with this example. If I'm doing hours of study and grade, so I'm just going to, make up a few data values here. So I had somebody who studied for 2 hours, got an 83. Somebody who studied for 1 hour, got a 74. Somebody else who studied for 1 hour, got a 79. Somebody who studied for 5 hours, got a 90. Somebody who studied for 3 hours, got a 92. There's just a few values. Again, I don't want to go too crazy here. We'd have to get some scale here. Here I have it set up. Hours of study is the X, and then grade on the exam would be your Y. I'm going to cheat a little bit just to kind of get up to these numbers. So I'm just going to jump. I really should have 10, 20, 30, 40. But just to make a little jump, because I should have given myself a tiny bit more room here. You use this little break to indicate you're making a jump, which you really shouldn't do here. I'm just trying to get to the top here so I could have test grades of 70, 80, and 90. My hours of study. And I would start plotting points. 2, 83, X is 2, 83 for Y would be roughly there. 1, 74 would be there. 1, 79 would be there. 5, 90 would be up here. 3, 92 would be up here. That's it. That's our scatter plot. That's all there is to it. Just literally putting them together. Now, later on, we will talk about the idea of positive correlation, of negative correlation, of trying to determine, is there like this type of a pattern or is there this type of a pattern? In this one, with this situation, this would make sense. The idea that we would speculate, at least, that the more you study, the higher the test grade you get. Now, it's not perfect. This person studied more than this person, but this person had a higher test grade than this person. So it's not a perfect scenario, but the overall trend, the further you go to the right here with higher numbers of study, the higher the point you would get by having a higher test grade. So that's something we'll get to. Like I said, I'm pretty sure that's chapter 5. We'll come back and see a little more of that. This would be a negative correlation, an inverse correlation, where as one variable goes up, the other goes down. So this would be like something like, how safe is your driving based on the number of alcoholic drinks you've had? The more alcoholic drinks you've had, the worse you've done. You know, and there's plenty of other situations. People talk about how much is your car worth and how many years old is it? Well, it starts off as this very high value, and the older it gets, the lower that value is. So there are plenty of situations that fit that. It's a little easier to think of these. But like I said, that's all. That's all we wanted to introduce here for this first part, just the basic scatter plot. The second one is a very specific situation, still bivariate in nature, but we can specifically look at a time series chart. Now we're specifically looking at something connected to time. So maybe how long has something passed, or maybe we're just looking at it by year. You know, maybe you're just looking at the year, the first day of the year, and you're looking at how much money, how much money is in your bank account. So in, 2010, you had $1,200. In 2011, you had $1,275. In 2012, you had $1,300. In 2013, you had $1,420. In 2014, you had $1,515. That could certainly be some type of information that we would see. Now, maybe you don't have data for every single year, but this certainly works. This is a common way that we see data paired together. We still plot it like we would a scatter plot. So I'd have year. So it's 2010, 2011, 2012. This, maybe it's not by year. Maybe you're doing it by month and you're going January, February, March, April, whatever. And then we have how much money is in the account. And again, just for kind of like what I did up here, once again, we will talk about the importance of on your Y scale, how misleading it is if you just jump to an important number. So again, just a lot of space. And then here we'll have 1,200, 1,300, 1,400, and 1,500. So 2010, we've got $1,200. We've got this point. 2011, we've got 1,275. 2012, we've got an even 1,300. 2013, we're all the way up to 1,420. Here's the difference. In a scatter plot, you literally just put the dots. That's it. You put the dots where they are, and that's it. I put these arrows to try and show the trends, but these are not literally a part of the scatter plot. But in a time series chart, our tradition is we always connect the dots. Not trying to get any smooth curve through here, just literally connecting the dots. Actually, let me make sure this goes down at some point. Let's say, so we had 2013, we're at 1,420. Let's say we went down to 1,315 in 2014. So I would come back down to about here. So I'm not just trying to just draw a random curve. I'm literally just connecting the dots from one point to the next. Now, that's it. That's all there is to it. Now, we have to be clear here that we only have the dots here, here, and here. So I'm not looking in the middle. I'm not guessing by the middle of 2010. So like by, July 2010, I'm not trying to use this to say, well, I've got about $1,220. I'm purely making the jump, but we just by habit connect the dots. So that's all there is for a time series chart. I mean, certainly we could do multiple of these. Maybe I use the black pen and this is, person A's bank account. And then I could use the red pen to show person B's bank account so we can compare them to each other. Maybe this person started below, flattened out a little bit, still stayed flat, but then still stayed higher here. Maybe we're trying to compare how these two people invested their money or something like that. But that's all there is to it. Just plotting the points and making sure we connect the dots. So that's it for bivariate. We'll finish up chapter 3 with the discussion. It's 3.5. They call it a little bit of the interpreting, but I really want to jump past that and get more into the idea of misuses and seeing how graphs and charts can mislead your audience.